apply on an object that has a tendency to change its own shape due to the application of force is proportional to the extension or the change in length that the object is going to experience. So if the force that is in newtons and extension that could be in millimeters, that could be in centimeters, and that could be in meters, depending upon what the examiner is giving the values for the question. So it is proportional. Now, there's one thing that we need to understand. Proportionality means that the graph will start from the origin. It has to start from the origin. Students sometimes confuse these situations as directly proportional as well. For example, if a graph is starting like this or is going like this from the negative or the positive axis, these are not proportionality graphs. These are just straight lines in which you can say that as x increases, y also increases, but you can't say that they are proportional. Proportional, or the word proportionality, is specifically reserved for the graph that passes from the origin, right? Okay, so up to the point where the line is straight, we can say that this is a straight line, and the equation that is f is proportional to e holds true, and we can use this equation in this region. So that's this region basically come to be known as the elastic region. Now, for example, you have applied so much force that the object has eventually deformed, and after the removal of the disturbing force, the object fails to come back to its original shape. So in that region, you cannot say that force is proportional to extension. You cannot say this any longer. And in this region, we will say that the object has permanently deformed, or you can say that this is not going to come back or regain its original shape. And in this, the one interesting bit is that this specific point, this point, is known as limit of proportionality. Now, mind you, this is a mathematical concept. It's not a physical problem. This point does not tell us whether there is a physical limit that has been reached. That physical limit is some other thing. That is elastic limit, which is not a part of your course. That is sometime after the proportionality limit. Basically, what happens is that after you've crossed limit of proportionality, what you can't do anymore is use Hooke's law. That is all, because the line doesn't remain straight anymore. That is it. It's not something related to some physical aspect that the object will not return to its original shape. But at your level, we do assume that if a limit of proportionality has been exceeded, the object is assumed to have permanently deformed. But in reality, in A levels, this will not be the case. There will be an extra point over here that is known as the elastic limit. Basically, that is the point that you need to cross, or you need to breach in order for that object to eventually be deformed, right? So up to that, before that point, up to O levels or IGCSE, we would be assuming that this is the final limit, this is the final point, after which the object is assumed to be deformed. Do we understand up to this point?
Yeah.
All right. So, but this is properly or purely related to simple maths, or the ability of you, the user, to use maths to solve this question. All right, so let's try to make an equation from this. We right now have force proportional to extension. Sometimes it is force proportional to x, but that's just a matter of different representation. It doesn't change the fact that we're still talking about extension. Okay, so if I want to make this into a proportionality, but I want to convert this proportionality into an equality, I'm left with KE. Now, we must have done this, or you must have done this in your junior grades, that if I say A is proportional to B, I want to convert this into inequality, I need to introduce a constant in this equation. Yes? Okay, so based on the same idea, we are also introducing a constant in this equation that holds both parties close together in a tight mathematical fashion. But here, that constant has a name. Sometimes we call this the spring constant, and sometimes in some books you will find it to be called as force constant. Basically, this factor only tells you whether the spring is a bit stiff or difficult to stretch, or if it's a soft spring, which is easy to stretch, right? That's all what it does. Okay, so let's analyze what K actually is. So from this equation, if I want to make K the subject of the equation, that will become F divided by E, yes? And the unit becomes Newton. For the sake of discussion, let's say I'm taking centimeters. So newtons per centimeters will be the unit of K. Now, what does this tell you? For example, I say that the spring constant of the stiff spring is 200 newtons per centimeter. And for this one, that is 50 newtons per centimeter. How can we define, or how can we judge based on just the values, whether this one is stiffer, this one is softer? Because if I look at the values only analyzing the units, I realize that I need 50 newtons of force to cause an extension of 1 centimeter in this spring or rubber band. What is that 1 centimeter of extension? Now, for example, if this is the original spring or case, applying a force eventually causing or leading the spring to increase its length by a matter of 1 centimeter. If I had done that by applying a force of 50 newtons, then that would be this spring. Yes? But for the stiffer one, I would have to apply a force of 200 newtons to still cause the extension of 1 centimeter, because it is newtons per 1 centimeter, the unit, of course. Yes? So which one requires more force for the same amount of extension? Is that the stiffer one or is that the softer one?
Obviously, the soft one.
More force is required with the softer one?
No, less force.
Less force is, I'm asking which one requires the most force or the highest force?
Stiff one requires most force, obviously. 200 newtons.
Exactly. So we can make this decision, or we can take this decision based on just looking at the value of the spring constant, whether this is going to prove a stiff spring or whether it's going to prove as a softer spring. There is no specific threshold which we can use to actually say, okay, this one is stiffer and this one is softer. Basically, the term is relative. It is making a comparison between 250. If I were to make a comparison between 500 newtons per centimeter and 200 newtons per centimeter, then naturally this one would be referred as the softer one, and this one would be referred to as a stiffer one. Do we understand this point?
Yeah.
So the terms soft and stiff are relative. They don't have anything to do with the real life example that yes, this is going to give me some visualization that what 200 newtons per centimeter may feel like in the real life. No, we don't have that. Okay, so we understand what is F, we understand what is extension, we understand what is spring constant and how it is associated in the real life by physical aspect. Let's try to solve an example of a question. Let's say that we have a spring right here that doesn't have any force on it. It's completely unloaded right now. And we have another spring right now with us that has or houses a mass of, let's say, 5 kgs. What we're required to find out for this spring is what would happen if this new mass is 7 kgs. So he will give us some values. Let's say some values are given to us. I will draw them on the screen right now. This value is given to us. This value is given to us. And what is being asked is this value. Now there's a difference between both values. Let's say this is 10 centimeters. This is 15 centimeters. And the rest of the question, we have to solve that. All right, so if you notice, the first situation gives you a complete set of information, but why does it do so? This is a complete set of information. This is complete info from this example and from this one. Why does it do? Why does it do that? It's doing that so that you can find K, right? So how do we solve or use this equation? The first job of any student would be to find K. Why? Because if we find out the proportionality constant or the spring constant, he can give us any value in the universe of force and extension. If we know the value of K, we can find the other value. It's simple mathematical principle, yes? So using F equals to KE, I can break it down as this. It looks like that the change of force is equal to K in a change of length. How much force have I changed? So that would be F2 minus F1 equals to K into How much length have I changed? L2 minus L1, which of course eventually becomes extension. That is the difference of both values, right? So the force that I have applied afterwards is 5 kg. The force that I had initially, that is nothing. So I will write 0 over there. But one more thing to be noticed is that this is force. We are dealing with mass. So what I need to do is convert this mass to weight. So this force will eventually be mg minus mg equals to k times length 2 is this one, the situation afterwards. That will be 15 minus the initial situation, that is 10. And of course, this is 0 because there's nothing over there. So we are left with nothing. So the equation finally becomes mass is 5. Of course, your course deals with the value of g to be 9.8.
Yeah.
But for the sake of your lessons, for the sake of my lectures only, I will be taking 10 so that we can conveniently solve these values without using the calculator. Okay, so the value is 10 equals to k, and after subtraction we get 5. So k is equal to 50 divided by 5, which is k equals to 10 newtons per centimeter. How did I find out the unit? I know that the force is being represented in newtons. Why did I write down centimeters? Because my whole question is in centimeters. Yes? If the whole question would have been in millimeters, I would have written down newtons per millimeter. Is that so? Right? All right. Okay, so I have done my first job is to find out the spring constant over here. The next step would be to find out the unknown information that the examiner is asking from me. All right, so there are multiple ways to do that, or multiple answers or questions that he can generate from the same situation. Let's look at that. So he's asking me about this extension. All right, no problem. I will still use the formula F equals to KE. Opening this up, this would be change in force equals to K change in length. Similarly, F2 minus F1 equals to K into L2 minus L1. Now, if you would notice what I've done is that first force dealt with first length and the second force dealt with second length. Yes? Similarly, over here, the set of values will still remain the same. F2 would be dealing with L2 and F1 will be dealing with L1. So the set of values should remain the same. So what I'm going to do, I see this is my F2 and this whole process, this whole length will be my L2. Yes? Of course, we can go towards direct extension as well. We will get to that later as well. And this will become my L1 for the second situation, and this will become my force 1 for the second situation. So F2 is 7 kg, so that will be 7 into 10 minus 5 into 10 equals to K, which I know by now is 10. So I will replace that value into L2, which I don't know. So L2 will be a part of the equation as it is. And L1, I'm familiar with, that is 15. Now, before solving the question, can you predict whether L2 will be greater than 15 or less than 15?
Okay.
Is this length going to be greater than 15 or not?
Obviously. Sorry.
Yeah. So why did I ask this question? I asked this question because if due to some algebra or some problem in mathematics, you end up with this answer smaller than 15, that means that you've done a mistake. Exactly. So you can go back and recheck the question, right? Okay, so we are left with 20 newtons over here. We have 10 into L minus 15. This will be taken over there. So this becomes 2 equals L minus 15. L comes out as 17 centimeters, right? So this whole length is 17 centimeters, but he was asking me about extension only. He didn't ask me about the total length. So to find extension, exactly. So L2 minus L1, that would be 17 minus 15, which is 2 centimeters. Yes?
Yeah.
This is the method number 1. If you had to find extension directly, what you could have done is use this method, that what amount of force do I need to spend to find this extension? That is fine. So what we would have done is that F equals to KE. How much extra force are you applying in this case? You've applied a force of 20 newtons as a surplus, yes? Moving from 5 to 7, you've given an extra force of 20, yes? And the value of K is 10, and E is what we need to find out. So E could have directly be found as this process. Because now you know this fact that how much extra did you added in the previous situation. So your change in this situation was an addition of 20 newtons of force. And that addition is actually going to cause this extension, which is the Hooke's law, that however amount of force you provide, that is going to consequently produce the amount of extension. So 20 newtons of force will extend my spring by 2 centimeters, which we found by a long method, and we also know a trick point to be used in P1 MCQs. It all depends on you, what method you want to choose, right?
Yeah.
There's no discrimination from the examiner that this is how you're supposed to solve it. It's completely your choice. Sometimes you do need to use this method to fully understand what's going on in the question. Sometimes you can directly, straightforward use this method and get to your answer, final answer. It doesn't matter. Do we understand what's this question and how do we solve it?
Yes.
All right. Okay. So the next topic that we have is a comparison of types of spring. Then I might show you a visualization of springs as well. Okay, so types of spring. There are two situations in which you will find this. The first situation is having springs in parallel, and the second one is having them in series. This topic is not directly related to you in your course, but I've seen questions from this, so I'm creating a separate heading for them. Series and parallel. So you may have seen the springs in these configuration before, but let's give them a name for now. So the first name is series and the second name is being parallel. All right. So what does this mean? It means that the springs are connected one after the other, like this, right? And in this situation, the springs would be connected right beside each other. Do we understand this?
Yeah.
All right. So we're going to start with a reference case. This is my reference case. Reference would mean single spring, single load, no problems, no issues. So this is my single spring and this is my spring that is loaded with some weight W, right? And of course, it is going to experience some extension X or E, whatever suits you. So this is my reference case. Why have I drawn a reference case? Because it's going to make my situation afterwards easy. All right, so if I connect my springs in series, what's going to happen to the extension? Can you predict if I had applied the same force? If this is 10 newtons, I'm applying 10 newtons over here. I'm going to make this constant throughout the experiment. My question to you is that if this is the extension, let's say the extension is 2 centimeters and the weight is 10 newtons, the examiner will not give you these values for an MCQ. He would expect that you can make this comparison in a variable form, right? Just by mentioning that it is going to extend 2E, 4E, 5E, or something like that. I'm giving you values so that you can make a reasonable comparison just for the class, right? So my question to you would be, if I add this weight to the situation, which is again the same W, that's for the reference case, how much extension should I experience for this case? Is it going to be twice as much? Is it going to be half as much? Is it going to be 4 times, 10 times? How much is going to be the extension?
Would it be lower? Like there would be less extension?
No, it will be more extension. Why? Because this weight is not only stretching this spring, it is also being experienced by this spring. So if this spring was alone, it was experiencing a force, or it was experiencing an extension of E. Now, every spring has experienced a little bit or tiny bit of extension because of this weight, because both of them have to carry it, no? So this is the second spring starting from here and a little bit of extension experienced by that spring, eventually moving towards my final weight. Yes, previously there was no weight, now there is some weight. So this tiny bit of extension comes from this idea. This original length is going to remain the same. That's not affected, right? So this extension is this part, the one that's not disturbed for both springs. But this little bit or tiny bit of extension is coming from the weight that is being experienced by both springs. Both of them are experiencing that. So, and it will be dealt, or they will be dealt if they were alone. So if the spring was alone, it would have experienced an extension of E. So that is why over here, they're both experiencing that. And To total that extension, the total extension would be 2 times E. Extension of this plus extension of that. So in the total length, I would experience twice an extension in comparison to the single case. Do we understand this?
Yes.
So a series combination will extend 2 times in comparison to the reference case, right? Now let's move towards, and of course it can be repeated in a manner. Right now we have 2 springs. What if we had 3 springs? So how much would be the extension in this case? It would be 3.
So it will be
If we had 4 springs, then the total extension would become 4, right? So there is a trend in this situation, which I've just explained to you. Yes?
Yes.
All right. So over here, we have a parallel combination. What happens over here is that whatever weight I add is basically shared between the 2 springs. Both of them will give half of that. Right? So if in this, coming back to this reference, if weight 10 causes an extension of 2, if I half this weight, or if I decrease it to half, only 5 newtons, would this not be extended to only 1 centimeters? Because I've halved it? No? Yeah. So since weight is being equally distributed over here, I will expect half an extension in both springs, because now the load is shared between both springs and they both are working together. Right?
Yeah.
So in this case, the total extension, the extension experienced by both springs, because both are connected, was only half. Right?
Yeah.
Because this has extended by, let's say, 1 centimeter. This has also extended by 1 centimeter. So the overall extension, since they're moving collectively side by side, they would only allow an extra length of 1 centimeter. Yes. So this extension of 1 spring is good enough to get the idea about the rest of the springs. Yes. So the total extension would become E by 2. And the idea still stands for a question that has, let's say, 3 springs. If the springs are 3, then the extension would be E by 3. If there are 4 springs, extension would have decreased by a factor of 4. Do we understand this?
Yes.
Any problems?
No.
All right. So what we are left with is that in this case, the extension has halved between parallel and my reference case. Now, can you make a comparison right now? Which one is softer and which one has become stiffer?
Can you repeat once more?
Yeah. Which one of the 2 situations, series or parallel, has caused my system to become softer? Which one of the 2 has caused my system to become stiffer or more? Right? So this one causes the system to become stiffer, and this one causes the system to become softer. That is how they design the suspension of vehicles. Whether they need 1 spring, whether they need 2 springs or 3 springs, the common vehicle that we have on the road only has 1 spring, right? But the larger vehicles or the vehicle designed for the track, they have more than 1 springs in multiple locations doing the same job, right? Okay, so one last question before we conclude the lesson today. Can you make a comparison between series and parallel? Can you make a comparison between series and parallel? How far away are they in terms of stretch? How much more the series combination stretches than the stiffer combination? It's like comparing 2E with E by 2. When we compare them mathematically, can we say that we're supposed to take a ratio? Yeah?
Yeah.
So my series spring ratio parallel spring, this one stretches 2E, this one stretches E by 2. And if I cancel out the E and I take this 2 over there, this becomes 4 ratio 1. Yes?
Yeah.
So that looks like that my series combination stretches 4 times more than parallel.
Yeah.
And my parallel stretches 4 times less than series. Do we understand this idea?
Yes, and this ratio will be constant in all cases.
In all cases, as long as there are only 2 springs.
Yeah.
If there are more than that, then you'll have to make a comparison or take a ratio like this one again. Yes.
Yeah.
We know that adding more number of springs will equally divide the ratio in this case. 3 springs, E by 3. 10 springs, E by 10, right? So it doesn't matter. It doesn't matter. So this will be series comparison. All right. So we understand the comparison between parallel and series and everything. Yeah.
Yes.
Any problems up to this point? No.
No.
All right. So I'm going to stop sharing the screen. Okay. So can you see the screen?
Yes.
Okay. So let me apply some force. Let's look at single spring over here. If I apply a force on the spring, let's say 50 newtons of force, and let me give you some values with the values. Can you see 0.250 on the screen? Yes?
Yeah.
All right. Okay. So I'm going to highlight other forces as well. The orange arrow represents the 50 Newton force that I have applied. The 50 Newton blue represents what's spring doing with you. So it's of course due to Newton's third law. If you apply a force, it will apply a restoring force in this case in the opposite direction. Because if you remove this 50 Newton force, it's going to go back, right?
Yeah.
All right. So now let's try to experiment. I am not changing the amount of force that's going to remain 50, but I will change the amount of spring constant. Do we see that over here? That is 200. Yeah. So let's see what happens if I increase the spring constant. If I increase the spring constant, notice how the displacement is reducing. It's reducing 0.125. Now it's reducing even 0.087 or something like that.
Then as that spring constant increases, you need more force to be able
to it's becoming more and more difficult to stretch the spring. Yes, even with the same amount of force, this is going to become more difficult. And notice one more change, that if I increase its value to maximum, the spring has become thicker. If I go back, the spring has become thinner. So the mechanical strength coming from the spring may be sometimes attributed to its thickness or how thick that spring is. Yes, for a visual reference. Do we understand up to this point? Yeah. Now let's include an equilibrium position. This is the equilibrium position. That would mean where would it go if there was no forces acting on it? So if I decrease the force to 0, this is where it would want to go, or this is where it will be. So this is the original length. If the question states unstretched length, that is this length. This is referred to as original length or unstretched length. Both words would mean the same thing. Yeah. All right. So let's keep applying the force. Let's say I'm applying a force of 50 newtons. Now I'm going to introduce a parallel system over here. So it's not.
So divide the.
Yeah, this one, right? So we are going to remove. We are going to stay at one spring. Now let's give this spring the same values. Over here we had so we had to give it 200 newtons because that is the spring constant over there. So let's say that I'm keeping the spring constants of both same. I will be applying a force of 50 newtons in this case as well to make a comparison, right? So displacement, equilibrium position, and values. Look, the value is 0.125, right? Over here we had 0.250, right?
Exactly half because they're two
exactly
springs.
Half, exactly half. If I go back to the comparison, we would remember that in the reference case, we had the springs half the value of the parallel case. But if I had an experiment, I don't have it right now with me, I believe. I think so. Yeah, I don't have the visuals for the case in which both springs are in series to each other. I don't have it with me. But if I had that one, whatever extension that would have, the system or this parallel system would have had an extension 4 times of that, right? This is the comparison that we did last time, yes?
Yeah.
All right. So do we understand what's happening over here and how the values are being calculated and what's spring constant and the applied force? Any issues up to this point?
No.
All right. So we understand what's what, and there's no problem in this lesson at least. We've revised this.